Hi, everyone. This is Algebra 1. This is Unit 5. We're talking about functions and the properties of functions. We're going to start with Lesson 5.1, where we talk about how to describe different sets of numbers. So um, when we talk about sets of numbers, we could have a set of numbers that's a finite set of numbers. So like if I just had the numbers, 2, 4, and 5, those three numbers would be a finite set. There's only a certain number of them, and I can point to each member of it and say there it is. Um, but where we run into problems is where we have what are called infinite sets. So if I try to describe all the numbers between, say, like -5 and +5, there's an infinite number of numbers in between those two things. So we're talking about how do we describe those mathematically. So mathematicians have three general ways of doing that. They use what's called inequality notation. They use another method called set notation, and then the last one is interval notation. So those are three ways of kind of describing the same thing. Inequality notation is what we've been using, what you've been using up until now. Interval notation is what we'll be using primarily moving forward, and then set notation is more of a more formal way of describing sets. So it's typically used in publications and things like that. So, um, so let's start off just by talking about some different sets of numbers. So we think about numbers just in general. When we start learning about numbers, generally we learn about numbers by counting things or pointing to things. We say, there's one duck and two kittens and whatever. Um, so it's a very physical, very direct, representation. The number one represents one of something, and so we call those the natural numbers. Those are the numbers 1, 2, 3, 4, 5, and so on. They don't include the number 0, and they don't include anything in between those. So it doesn't include fractions or decimals or anything like that. It's just those natural counting numbers. Those numbers referred to sometimes just using the letter N for natural numbers. And then sort of as we get a little more sophisticated, we can start thinking about that concept of 0. And the concept of 0 and the number 0 are actually, fairly recent additions to the world of mathematics and kind of the history of mankind. Um, but that idea of being able to point to an empty space and saying, oh, that's the number 0, right, is kind of an odd thing. So they started introducing that number 0 when they started using kind of the base 10 counting system, so that 0 represents the a placeholder for the ones space or the 10 space or the 100 space. So uh, so that number 0 is what's included in the whole numbers. So the whole numbers include all of the natural numbers plus the number 0. Okay, and the whole numbers are often referred to as W. And then the next kind of numbers that get added to our sort of definition or our sets of numbers are what are called the integers. The integers include negative numbers. Okay, so negative numbers, and this all came about as a result of like commerce. Okay, so the idea of having a debt or owing somebody something or having less than 0 amount, right? Um, that's where the negatives came from. And so when we talk about the integers, we're talking about, again, those kind of counting numbers, but we're also including 0, and then we're including the negative or the opposite of the natural numbers. Okay, we still don't have any fractions or decimals or anything like that. We're still talking about just, those whole pieces of numbers and zero and the negatives. Integers are sometimes referred to by the letter Z. And then we start looking at the numbers in between the integers, right? So between 0 and 1, for example, I can talk about halfway through there. So that idea of a half or a fraction is what's called a rational number. So a rational number is any number that can be written as a fraction. And when we say written as a fraction, we mean a fraction with an integer as the numerator and an integer as the denominator. All right. So if I had 0.2 over 0.7, that's not necessarily a rational number, but we could write that as 2 over 7. So when we talk about those rationals, we're talking about those integers, or it also means division, right? So the thing about rational numbers is that they can be represented as a fraction. So for example, 3 over 4, but we can also represent that as a decimal number. And so if we divide 4 into 3, right, we divide 3 into 4, 4 into 3, right, we get 0.75. Okay, and it stops at that point. So we can represent those as a fraction, but they also have a decimal representation as well. If we look at the example of 1/3, that gets kind of into a strange area, because when we divide 3 into 1, right, and we go through that division algorithm, right, process, we find that we get this 0.3, and then there's a little bit left over, and so it keeps going. This 0.3333333, and that 3 repeats just on and on forever. That number can also be written as a fraction, but it has that repeating part to it. Okay, so that will be represented by this bar over the 3, or sometimes it's represented as a dot over the 3. So that represents a repeating pattern in there. So, but we can represent that as 1/3 as a fraction. We can also represent it as a decimal, even though this decimal is an approximation, right? It's not exactly 0.3, it's 0.3 plus a little bit more. And then again, we're kind of looking at that space in between the integers. We come across some numbers that just don't behave like rational numbers. They can't be written as fractions. And when we do the division on them, right, when we calculate their values, that decimal part never ends. And not only does it never end, but it never repeats. There's no repeating patterns in those numbers at all. And so since those numbers don't behave like rational numbers, they call those irrational numbers. So irrational numbers, they're numbers that can't be written as fractions. So they're decimal numbers. They can't be written as fractions. Those decimals don't ever repeat. So there's no pattern of numbers in those decimals that ever repeats. And it doesn't end. Okay, so we'll just keep dividing and dividing. Like we can just keep calculating values, and we'll just keep going on and on forever and ever and ever. Some examples of those are, for example, the square root of 2, or the number pi. So those are both considered irrational numbers. And in fact, when we talk about square roots, the square root of any prime number would be an irrational number. So the square root of 3, the square root of 5, the square root of 7, and so on. Okay. Those are all considered irrational numbers. So they have that property where they can't be written as fractions, the decimals don't repeat, and it never ever ends. Okay, so they have those special properties. So if we look at the collection of all of those things, right? Irrational numbers, rational numbers, and remember that the rational numbers includes all of the integers, it includes all of the whole numbers, it includes all of the natural numbers. So we look at this set of rational numbers and irrational numbers. We call that the set of real numbers. If we talk about a number line, right, where we have all the numbers, right, all the real numbers written out, or all the real numbers are represented on that line, we call that the set of all the real numbers. Okay, so includes all the rational numbers and all the irrational numbers. Now we have this set of real numbers that's often referred to as R, but that's not all of the numbers. Okay, there are actually other numbers that are out there, and we have those numbers, and they have this property where they like kind of work mathematically, but there's not like a logical representation of them. So the example of that is the square root of -1. If I try to take a number, right, and multiply it by itself to get -1, there's no way that I can do that. Okay, I can't multiply a number with itself and get a negative number. So this idea of a square root of -1 pops up when we do math, when we work some problems, but it just doesn't make any sense. They call that an imaginary number. It's also referred to as a complex number. C. So we're not going to really deal with imaginary numbers at this point. In Algebra 2, we'll talk about those a little bit more. But we're going to be looking at the real numbers. We show this as kind of a Venn diagram. You can kind of think about it this way. So we have this set of complex numbers, right? Complex numbers, real numbers can be written as complex numbers and imaginary numbers. Again, we're not going to focus on that a whole lot, but we can take all of the numbers, right, and kind of break them into two groups, imaginary numbers and real numbers. And again, we're going to focus on this set of real numbers. The real numbers can be broken down into two sets, right? They can be broken down into irrational numbers and rational numbers. And those rational numbers represent, all the integers, and the integers include all the whole numbers, and the whole numbers include all the natural numbers. So if I look at, say, for example, the number 3, okay, well, 3 is a natural number, which is also included in the whole numbers, integers, the rationals, and the real numbers, okay? So 3 is a member of the real numbers, it's a member of the rational numbers, it's a member of the set of integers, whole numbers, natural numbers. 3 is not an irrational number. Okay, so 3 is not a rational number. If I look at, for example, 0.142, that repeats. So that 142 would repeat, right? So again, that would not be a natural number. It's not a whole number. It's not an integer, but we could represent that as a fraction. That's a rational number. Okay, it has a repeating part to it, and it can be written as a decimal. So that is a rational number. It's not irrational because of this repeating part, and it is considered a real. So this number here would be considered a member of the real numbers and a member of the rational numbers. Okay, so you'll see some problems like that where they ask you, they'll give you a number and they'll say, what sets did this belong to? And so you can go through and figure out what those are. Okay, so when we start talking about sets of numbers, right, we can talk about these kind of broad sets of numbers, these well-defined sets of numbers, but then we also have other sets of numbers, they're kind of subsets of these, right? They're parts of these numbers. And so we have 3 different ways of kind of notating those, right? Of talking about those or writing about those. And so the first method we have are what are called inequalities. And this is what we've kind of typically seen, right? So if I want to look at all of the values that are greater than 5, I can say, well, these are all the values, and we're going to use x to represent all those values. And it's all the values, all the numbers that are greater than 5. So it doesn't include 5, but it would include like 5.01, 5.02, 5.0001, right? Anything that's bigger than 5. And if I represented that on a number line, I had a number line, I said, well, this represents all of the real numbers. This number line represents all the real numbers. Somewhere in here is 0, okay? And I have negative numbers to the left of that, and I have positive numbers to the right of that. I could say, well, if this is 5, then when x is greater than 5, it represents all of the numbers to the right on that number line, okay? And it doesn't include 5, so we're going to put an open circle there. So we've graphed these inequalities, right? So that's how that would be represented as an inequality. We can also have compound inequalities. So this is all of the numbers that are greater than -10 and less than 5. So this is what's considered an and. So it's actually two sets of inequalities. It's all the numbers between -10 and +5. Notice that it includes -10, but it does not include +5. And we can also have what's called an OR. This is another type of compound inequality. So I can have all the numbers that are less than or equal to -10, or the numbers that are greater than 5. And so I can make a set out of all those numbers. So they're either in this side, less than or equal to -10, or to the right of +5. So that's inequality notation. If I were to talk about the set of all the real numbers, okay, the way that I would write that is I would just say R. This R, this capital R, and they typically will write it as this kind of fancy, double bar R. This represents all the real numbers. Okay. And this goes back to those definitions of those numbers, right? All the real numbers are represented by R. Right? The irrational numbers are represented by I, and they would represent that as like a double bar I. The rationals are represented by a Q, and it would probably be a double bar Q, something like that. Okay. So they use those kind of fancy versions of those letters to represent those sets of numbers. Okay. So we would just say that this set of numbers is all of the real numbers. Okay, let's jump over here to set builder notation. So set builder notation is kind of a fancier or a more formal way of describing an inequality. Okay, so it's read very specifically. These curly brackets right here means the set of. Okay. So whenever we see curly brackets, that we're talking about the set of numbers. So we're talking about a set of numbers that are represented by the letter X. So the set of numbers X. And then this bar right here says that it means to have these properties, right? Or they could say such that. So this is the set of all the x's such that the x's are all greater than 5. All right. So that's how we would read that. This is the set of all x's such that x is a member of, that's what that little E kind of thing looks like, that says that x is a member of the real numbers. Okay, and we have some other symbols down here that they use. The set of all x's such that x is greater than or equal to -10 and x is less than 5. So we have this symbol here means and. Or we can have the symbol or. There's another one that's union. There's some other symbols that you come across. But like I said, it's more of a formal way of describing these sets of numbers. Generally, what we care about, right, when we're working is we just care about this inequality inside of here. Okay, so we're not going to write these a whole lot, but we will come across them, and we will have to know how to read them and understand them. Okay, so the last set we're going to look at, or the last kind of notation we're going to look at, is what's called interval notation. Interval notation is just kind of a shorthand way of describing numbers. And so what this means is that it goes from the smallest value to the biggest value, the smallest value to the biggest value, the smallest value to the biggest value. So it means all the numbers from 5 to infinity, all the numbers from -10 to 5, all the numbers from negative infinity up to -10, all the numbers from negative infinity to positive infinity. We're talking about this interval. Okay, it's the numbers between these two numbers. The smallest number is always on the left, and the largest number is always on the right. Now, let's talk about that in a little more detail. When we talk about interval notation, like I said, it's always talked about in terms of two numbers, right? The smallest number, right? Or you can, on the number line, it would be the left side, right, of the number line, and then the largest number, or the right side on that number line. We put a comma in between them, and then we use brackets to determine what happens at those endpoints. Okay, so if I had some numbers that included, like say if I had from 5 to 8, and I wanted to include the values 5 and 8, right, I would say 5 comma 8, and I would use square brackets on that. Right? If I did not want to include those numbers, if I wanted all the numbers between 5 and 8, but not including 5 and 8, I would use round brackets. Okay, and then we use these infinity symbols. So we'll use negative infinity. This represents on a number line, it represents all the numbers going to the left, right, of 0. All the numbers on the left side. It means it goes on forever and ever and never stops. And positive infinity, or sometimes it's just written as infinity, that means all the numbers to the right. It keeps going, the numbers keep getting bigger and bigger and bigger, and it never ever stops. All right, so let's look at an example here. So I want to describe the set of all the numbers between -5 and +2. And I want to include -5, but I do not want to include +2. So I'm going to start with the smallest number. So the left side of that would be -5. And then I want to go up to the biggest number, which is 2. Okay. Now it can include -5. So because it can include, I'm going to use a square bracket, but it will not include +2. So I'm going to use a round bracket. Okay, so round bracket means not including, square bracket means includes. And we can mix and match those brackets in however we need. Look at another example, all the numbers less than or equal to 3. So if I think about a number line, right, the left side of that is going to be 3. And it's going to be all of the numbers that are less than that. Sorry, I made a mistake there. I want all the numbers that are less than that. So on the left-hand side, right, if I think of this as a number line, if this is 3, I want all the numbers that are less than or equal to that. So I want all the numbers to the left of that. Okay, so the smallest number, well, there is no smallest number. It keeps going, forever to the left. So we say that's negative infinity on the left side. On the right side, it stops right here at the +3. So there's my right side is +3. Okay. It can be equal to 3, so I'll put a square bracket on that. And then whenever we use an infinity sign, we're always going to use a round bracket with that. This infinity is a concept, right? It's not a number, it's a concept. It means that it keeps going forever and ever. So it will never equal infinity, right? So we're always going to use a round bracket on that. If I want to describe all of the real numbers, well, that would just be the number line, right? It would be all the numbers on the number line. So the left side, there's no end on the left side. It keeps going on forever and ever. So negative infinity. And on the right side, it also keeps going on forever and ever. So we can use infinity or positive infinity. And then we always use round brackets on those positive infinities. So in interval notation, this is how we would describe all of the real numbers. So here's some problems. You'll see some problems like this. So here they give you a graph and they want you to write the set of numbers as both an inequality and interval notation. So as an inequality, I start here at -1 and I want all the numbers to the left of that, so less than -1. I have an open circle, so that means it can't be equal to it. So I would say x is going to be less than -1. That's how I'd write that as an inequality. In interval notation, well, if I look at the left side of this, it goes on forever. So I'm going to say -infinity. And for the right side, it's going to end here at -1. So for my right side, it's going to be -1. I've got an open circle here, so that's going to be a round bracket. It can't be equal to -1. And because we have an infinity, we'll also use a round bracket there. Okay, so 3 different ways of describing that set of numbers. So here's another example. They want you to graph this. So this is using set builder notation. So if I were to read this, I would say this is the set of all numbers x such that x is between -4 and +3. Okay, so x is greater than or equal to -4 and less than 3. So if I were to graph that, I'll call this 0. And so -1, 2, 3, 4. So here's -4. And here's +3. And so I'll have a circle at -4. And I want the numbers in between -4 and +3. And it can be equal to -4, right? So I'm going to color in that circle. That's going to be a solid circle. Okay, so all the numbers between -4 and +3. If we were to write this in interval notation, we would say -4 is the smallest number, 3 is the biggest number. I've got a closed circuit, a closed circle, or an equal sign here. So I'm going to use a square bracket on the left side. On the right side, I have an open circle, right, or just a less than, and so I'm going to use a round bracket. Example 3, it asks you to write the following set of numbers using interval notation. Interval notation, so these are all the values of x that are greater than -5. So the smallest, if I were to graph this, right, this was -5 right here, right, maybe this is 0 right here. So I would be looking at all the numbers to the right of -5. It can't be equal to -5, so I have an open circle there. So in interval notation, I would say, well, my left-hand side of that is going to be -5. My right-hand side goes on forever, so that's going to be +infinity. And then I've got an open circle here, so this is going to be a round and a round. Okay, this takes a little bit of getting used to, but I think you'll find that the more you work with it, you'll find that interval notation is a very convenient and a very concise way of describing, an infinite set of numbers. So we'll go ahead and stop the lesson here for today. Take a look at the exercises, and please let me know if you have any questions.